confused the slide. Okay, so welcome you all to take part in the second gauge gravity talk of the season 3. This is our online seminar series which focus broadly on the diverse topic on gauge and gravity theories. And these seminars are roughly held once a month, preferably on Wednesdays. And the talks are recorded and uploaded on the CHEP YouTube channel. So some introduction to the audience, they will be muted during the talk, and the members, they can ask questions either by raising the hands or putting it in the chat box or just interrupting the speaker directly. So today's speaker is Professor Olga Papadoulaki. She did her master's from DAMT Cambridge. She did a PhD from Utrecht under Professor Umut Gursoy. And thereafter, she held postdoc position at Southampton, ICTP, and Perimeter Institute. She is currently a faculty at École Polytechnique, CPHT. And today she will talk us about an inflationary cosmology from ADS wormholes. Olga, over to you.
Thank you very much for the introduction and for inviting me to give this talk in this seminar series. So today I will talk about an inflationary cosmology from anti de Sitter wormholes, and this talk is mainly based in these two papers that I wrote in collaboration with Panos Begios, who is a postdoc at Ghent University, and Ioannis Yalamas, who is a postdoc at Tallinn. And if time permits, I will also discuss very briefly some work in progress with Panos and Ioannis, as well as with my student Paul Giringeli. So let's start by introducing briefly the history of our universe. So currently we believe that our universe started from a Big Bang. And then after a very small fraction of time, inflation started, and quantum fluctuations that were small became large and started freezing out as the space started expanding very fast. And this led to the development of large structure in our universe, such as our galaxies and our planets. Currently, our universe is expanding due to dark energy. It is hot and is extremely uniform at large scales. And we have a very good understanding from experimental data of what happened from inflation and after. But it's not clear how everything started and how we were led to inflation. So there are various features or problems of the cosmic evolution that inflation, a theory of inflation can explain very well. For example, some of these main problems were the flatness problem, where we observe that the matter and energy density in our universe has the critical value for our universe to look almost flat, homogeneous, and isotropic. So this seemed this seemed to be some fine-tuning on the initial conditions of the universe. But because of inflation, we can basically start from a universe that is very curved, but inflation then dilutes these initial conditions and leads us to the flat universe we observe today. The horizon problem, where we see causally disconnected regions of space-time to be very similar. And this can only be explained if they started all from a very small region of space-time, like after Big Bang, and then they, due to inflation, they very fast went to places that are causally disconnected. The monopole problem, where grand unifier theories predict that we will have a proliferation of exotic particles such as monopoles, but this is not what we observe. So if inflation started below the temperature where we have monopole creation, this can be explained. as well as it explains the fact that we see that primordial perturbations are nearly scale invariant. Currently, we have many experimental data that can rule out some theories of inflation, but there are still many theories of inflation that can describe very well the experimental data. There are many questions, though, especially related to pre-inflationary issues. For example, what gave rise to such initial conditions for inflation to start? Since we believe that our universe started from an initial singularity, the Big Bang singularity, there we would expect that the semiclassical laws of physics cease to exist. So we will need it seems that we will need a complete UV theory of gravity to understand questions related to the initial conditions of the universe. But is there a way to compute approximate or estimated probabilities and features of the early universe cosmology using semiclassical theory? So Hartle-Hawking actually gave one such appealing proposal for computing the wave function of the universe based on the so-called Wheeler-DeWitt equation. In this approach, one uses the canonical Hamiltonian formalism of general relativity and promotes the constraints expressing diffeomorphism invariance to quantum operators that annihilate the wave function. So let me briefly review the canonical formalism. So the basic idea is that the space-time is foliated into a family of space-like three-dimensional, in our case, hypersurfaces. Let's call them sigma t at its time coordinate t. And the coordinates on each slice, we represent them with xi. And in this setup, the dynamical variables are the metric tensor of the three-dimensional spatial slices, let's call it Gij, and their conjugate momenta pi ij. Now, using these variables, it is possible to define a Hamiltonian and thereby write the equations of motion of general relativity in the form of Hamilton's equations. To do so, it's very useful to use the ADM decomposition for the metric. So we write our four metric in this form, where n is the lapse and encodes the proper time evolution, and I is the shift vector and encodes how spatial coordinates change between hypersurfaces. And as we mentioned already, Gij is the metric on the slice sigma t. Now we start from the Einstein-Hilbert axiom with some matter. And in the ADM parameterization, we can write the canonical Hamiltonian in this form. Where H is the Hamiltonian constraint and Hi is the momentum constraint. That they have this form where pi ij is the conjugate momentum to the spatial three metric Gij. And with H and Hi matter, we symbolize matter contributions, and Di is the covariant derivative with respect to the covariant to the Gij metric. Now we know that gravity is diffeomorphic invariance. So it's a Gates theory. Thus, the physical states or configurations, they should be independent from the choice of the lapse and the shift. And this leads to constraints, the so-called Hamiltonian momentum constraints. So classically, this should be equal to 0. Now, if we also include a matter field, let's make it a scalar field, since later on this will play the role of the inflaton. And we want to go also at the quantum level, one imposes these constraints by annihilating, they promote them to operators, and essentially they act on the wave function or the state, and they should annihilate. And this leads to some functional differential equations, but these are not very well defined. But luckily, there is some truncation or ansatz, the so-called mini superspace ansatz, that is better defined and leads in the well-defined ordinary differential or partial differential equations. Fortunately, because our universe is isotropic and homogeneous, it's justified to use such an ansatz. Now let's see what is this mini superspace ansatz. We start from writing again the metric in the ADM formalism. We see that the shift is 0 and the three-dimensional hypersurfaces are three spheres. And the lapse and the scale factor and the scalar field depend only on time t coordinate. In this case, the Hamiltonian constraint is automatically satisfied, and the momentum constraint is automatically satisfied, and the Hamiltonian constraint leads to the Wheeler-DeWitt equation and becomes a well-defined PD.
Hello.
Yes.
Oh, can you go back to the earlier slide?
Yes.
So why you say so that these functional differential equations are not well defined, but they become well defined once we do mini superspace truncation? I didn't get that point. Sorry.
Yeah, it's true. First of all, because they are functional differential equations. You see, the psi and the h, they depend on g that are and pi that are functions of the space-time. And also, these operators are unbounded from below.
So unboundedness is what making them not well defined.
But also that because they are a functional differential equation, what it means to have functional differential equations. It's not a PD or an ODE that.
Okay. Yeah.
Okay. Now do that we have a well-defined PD, we can give appropriate boundary condition and in principle solve it. So Hartle-Hawking gave such a proposal, the so-called no-boundary proposal, that states that one has to make an excursion to Euclidean signature and consider compact metrics with no boundary at early times. And the resulting state or wave function corresponds to the Bunch-Davies or Euclidean vacuum, which can be thought of as the analog of the Minkowski vacuum when you have a positive cosmological constant. There is also an alternative proposal by Linde and Vilenkin, the so-called tunneling proposal, which is defined essentially by an influx or outflux of probability in the superspace of all metrics that leads to tunneling to our universe. But this we will not discuss in the following. We will focus more on improving or changing a bit the Hartle-Hawking proposal. Now let's see the simplest example, which is to have an empty de Sitter. So we consider the Einstein-Hilbert action with a positive cosmological constant that admits an empty de Sitter solution. And essentially what the Hartle-Hawking proposal tells us is that it describes a complex metric where we have half of Euclidean de Sitter, which essentially is a half sphere, glued to half of a Lorentzian de Sitter. So essentially, we are in the complex tau plane. We have a Euclidean time up to pi half, and then we analytically continue to Lorentzian time. And we get from the half sphere de Sitter, Lorentzian de Sitter. Now let's see how we can solve semiclassically by using WKB approximation, the Wheeler-DeWitt equation in the mini space, in the mini superspace approximation. So the Wheeler-DeWitt equation using the mini superspace ansatz with a positive cosmological constant no matter acquires this form, where A is the scale factor and pi A is the conjugate momentum to the scale factor. And to understand its semiclassical properties, it's very useful to use the WKB ansatz. Now here we have the plot of the Wheeler-DeWitt potential as a function of the scale factor. We see that for large values of the scale factor, the potential is unbounded from below. So we have an oscillatory solution for the wave function. So it's given by this. Whereas for small values of the scale factor, we can have bound states, and we have the Euclidean solution. And we have two options depending on the boundary conditions we impose. So the no boundary proposal selects the increasing branch, and the wave function vanishes for the zero value of the scale factor, whereas the tunneling proposal selects the decreasing branch. Now let us include also the scalar inflaton field, and moreover to assume a slow roll approximation for the potential in the inflationary region. This essentially means that the first and the second derivative of the potential with respect to the inflaton over the potential is very small. So essentially here this is nearly flat, nearly constant. So the Wheeler-DeWitt wave function, now that we included also the scalar field, depends on the scale factor and the scalar field. And given the wave function, we can compute the probability for a specific history or realization of the inflating universe via computing the norm squared of the wave function. Now let's see what this gives us for the no boundary and the tunneling proposal in this roll approximation. So essentially, we have these two solutions depending from whether we choose the no boundary or the tunneling proposal. And the
Olga,
probability, yes?
I think there's a question in the chat box.
Okay, I don't see the chat box. Let me maybe go out from. Maybe you can read it.
Can
Because
you confirm what gauge choices you take for the labs? Is it n dot equal to 0?
no, you don't choose a gauge here. Sorry, I'm trying to.
Subhashish, can you ask the question
Yeah.
directly?
So my doubt was,
Okay.
if you're using Wheeler-DeWitt equation, you must be using n dot is constant. Otherwise, you get a delta function on the right-hand side. So,
Sorry, but this is just.
I mean, if you don't take n dot is 0, then you are essentially talking about propagators, not the Wheeler-DeWitt equation.
Yeah, but the Wheeler-DeWitt equation does not include n, right? You can essentially comes from this part, right? You see.
Okay, so you don't take any gauge. Okay, fine.
No.
Okay.
Okay. So we have the we have the wave function for the no boundary and the tunneling proposal, and the probability essentially is given by the Euclidean, the exponential of the Euclidean non-shell axion, which we can compute and has this form, and the Lorentzian part is given by this expression. And usually the value of the inflaton or the size of the sphere is typically set at the horizon crossing during inflation. Now, apart from computing the wave function, we can also compute fluctuations and actually homogeneous fluctuations of the metric, of the three-dimensional metric and the inflaton. And the no boundary proposal predicts the correct spectrum of primordial perturbations that has a Gaussian suppression factor. So this points that the no-boundary proposal gives us really the cosmological vacuum. Whereas for the tunneling proposal, because the sign is the opposite, the fluctuations are unsuppressed. Now, let's see how the no-boundary proposal fits with stochastic inflation. So assume a roller inflationary scenario, and we split the evolution of a scalar field into UV and IR modes with respect to the Hubble scale. The IR physics at scales delta T analogous to the inverse of the Hubble scale and delta L much larger to the inverse of the Hubble scale is governed by an effective stochastic equation of this form. This part gives the classical evolution, and the quantum effects are in this stochastic variable psi. And we also have a Fokker-Planck equation for the probability that the field has the value phi at time t. Now, for a potential bounded from below, one finds an equilibrium J equals 0 distribution that is consistent with the no-boundary proposal. So this gives us a hint that at least in an effective description, the no-boundary proposal is relevant. Now, there are various issues with the no-boundary proposal. So first of all, if we have the wave function, we can compute the probability for a specific realization of our universe, as we said, via computing its norm squared. And this comes from the leading semiclassical piece of the wave function and indicates that the wave function is non-normalizable. Now, perhaps this is not a deep problem due to the mini-software space and the WKB approximations that we took. And we shouldn't expect that this computation is fundamental. And since it agrees with the stochastic description, this just points us that this is just an effective description of the IR sector. And there is no fundamental reason to demand the normalizability of the no-boundary wave function. Nevertheless, even using it in this restricted effective description sense, there is a more acute problem for the no-boundary proposal in the context of inflation that was very nicely reviewed in these two reviews by Lehners and Maldacena relatively recently. Now, the problem is the following. Remember the current cosmological constant problem. That the cosmological constant we observe is much smaller than what we had expected from computations. Now, this problem for the no-boundary proposal is exponentially worse because essentially this shows up here in the exponent. And essentially, this tells us that the no-boundary proposal gives us an overwhelming probability for an ethical universe with the smallest allowed number of for the cosmological constant. And also in the inflationary context, it predicts the least number of defaults. So essentially, it doesn't like to start here, but here. So the issue stems from the fact that the on-cell action for the positively curved Euclidean de Sitter is negative. So minus here with this minus combines and gives something positive here. So there are various ideas for how we can evade this problem. One possibility is instead of choosing the no-boundary proposal to choose the tunneling wave function, which evades this issue because here there is a plus instead of the minus. But the problem with the tunneling proposal is that, as we saw, it doesn't describe correctly the cosmological fluctuations beyond mini superspace, since they are getting enhanced. One could argue that we need to use some anthropic reasoning or selection rules, so we have to multiply with some factor our probability to make sense. Another explanation is that since the gravitational path integral is not well defined and gravity is non-normalizable, and we have also the conformal mode problem, maybe it's too naive to just take the Hartle-Hawking contour, but instead we have to use Picard-Lefset's theory and define an appropriate steepest descent contour in the field space and make it properly, and people work on this. Another explanation could be that if we include quantum effects and non-perturbative effects, these will dramatically change the wave function, and the behavior will be quite different from the naive semiclassical result. And this is something we observed in two-dimensional model. Or we could change entirely the assumptions and the initial setup that gave rise to our cosmology and see what we can get. Now, let me go a bit to negative space-times with negative cosmological constant. So in this case, the no-boundary proposal, or the analogous of the no-boundary proposal, works very, very nicely. For example, through the asymptotic correspondence, we have noticed that, so imagine we have Euclidean, global Euclidean ADS4, then boundary is an S3, and we can compute the partition function of the CFT on the S3 and the on-cell action from for the Euclidean ADS4. And we find that both sides match. And if we have also supersymmetry, for example, if we are in the EVGM theory, we can even match them at finite 10. And the crucial difference between ADS and the sitter is that the on-cell action for ADS is positive after one performs holographic renormalization. So we don't have this issue that we saw that the probability for the sitter is much larger than 1 and doesn't make sense. But the problem is that this scenario is not directly related to cosmology by just performing analytic continuation between Euclidean and Lorentzian time. One can consider to take a different contour than the one by Hartle-Hawking. For example, it seems that if we start from a minus Euclidean ADS space and we analytically continue, we get the sitter. But it's not clear what we mean when we take a negative Euclidean ADS space physically. Another approach is to use the domain wall cosmology correspondence put forward by Skenderis and Townsend, where you need to do multiple analytic continuations. But here we wish to retain a clear understanding of what is Lorentzian, what is Euclidean sectors, and relate them with a simple analytic continuation in time coordinate. And to do so, I will have again to go to negative space-time with negative cosmological constant. So in ADCFT, there is an example that can give rise to FRW cosmologies, and that is if we have a two-boundary Euclidean ADS wormhole. Such a space can be has a metric of this form, where the three-dimensional spatial metric is 3 sphere. And the scale factor has a local minimum at the Z2 reflection point, so at 0. And the two asymptotic boundaries are at plus and minus infinity, and they asymptote to Euclidean ADS. Now, if we analytically continue this Euclidean wormholes, we don't get black holes, so geometries with horizons, but instead, if we analytically continue the radial or the time direction, this gives rise to a Bank-Ranch cosmology. So here, upon analytic continuation, we have a local maximum. Now, the issue with this is that upon analytic continuation, they inevitably crunch, so they don't allow for a period of inflation. So to amend for this, we want to combine this idea with the no boundary proposal. So in the no boundary proposal, we started from a Euclidean de Sitter or sphere, and we cut it in the middle, and then we glue a Lorentzian universe that can expand. Now, in the example where we were starting from Euclidean ADS wormholes, again, we cut at the middle, at the Z2 reflection point, but inevitably here we have the cosmology crunches. So to evade this, what we should do is we start from an asymptotically Euclidean ADS wormhole. At some tau mean, it has a local minimum, but then it opens up again and resembles to the Euclidean de Sitter, and at the Z2 reflection point, that is now a local maximum, we analytically continue. And this will allow for inflation. Now we call this construction wine glass ADS wormholes, and they do exist also asymptotically flat analogs of those. And more clearly, their defining properties are the following. They should asymptote to Euclidean ADS spacetime at tau plus minus infinity. And in addition, at the Z2 reflection point at the middle, they should have a local maximum. And also the velocity of the scalar should be zero at that point. And these are also good initial conditions for subsequent inflationary evolution, since upon analytic continuation, the second derivative of the scale factor is positive with respect to time. Now, a pictorial example of such a scalar potential that can support such solutions is this. So here we have the potential is negative, and then it becomes positive, and we arrive here. So this is the Euclidean preparation, and from here we analytically continue to Lorentzian time, and we start, depending on the potential, we can start with good initial conditions for inflation to happen. And now, okay, these are all ideas. Is there an actual model that could realize such a potential? So a simple model is the following. We will consider an Einstein scalar action system of this form. And we have a spherically symmetric and homogeneous ansatz for the metric. And this is the three-form dual to the action field. And Q is we start with a constant it's the constant charge of the action field. And for this action, we find these two independent equations of motion. And this equation here, that is the equation for the scalar field. Essentially, we see that it describes a particle that moves in potential minus v of phi with a friction notification term depending on the sign of A prime over A. Now, to find the wormhole solution, we consider a potential for the scalar field v of phi that has a local maximum at the Z2 reflection point phi equals 0. For example, it can scale like this. And this leads to a normalization group flow that is driven by a relevant operator with conformal dimension delta. And here we can see the Euclidean evolution of the scale factor and of the scalar field in the minus v of phi potential. So here we have the plot of the scale factor as a function of the Euclidean time. So we see that for the part that A prime is negative, essentially the manifold shrinks. We arrive at a local minimum at tau mean. And then A prime is positive, so it expands again, arriving at tau equals 0 at a local maximum, having the value A max. And this causes the scalar field to first accelerate up to tau mean, and then starting accelerating, arriving at some value phi naught at tau equals 0, where it stops. And here we have the plot of the minus v of phi as a function of phi. I see questions. So the question is, does one have to add some energy momentum density at the section where the gluing of the space-time is done with the ds space-time? No, but you should match the two geometries there. And the fields, of course, everything, not like matter and like you want to have to be these functions to be continuous. So you want their first derivatives to be smooth. You don't want to have jumps there. Now, okay. Okay. So as we said, this is the description up to tau equals 0, where we are, so it's the Euclidean preparation. And then we analytically continue, and the potential should also contain a slow roll region for phi bigger than the value phi naught at tau equals 0, in order for the universe to be able to expand in Lorentzian time. And our proposal can accommodate various options that are consistent with the latest experimental constraints on inflation, and these are incorporated in the exact shape of the potential. Now, what this change of initial conditions buys us? So again, we can compute the semiclassical probability by computing the norm squared of the wave function for this model and compare it with the no-boundary proposal. So since we were working in this semiclassical WKB approximation, we just need to compute the Euclidean on-cell action. And we need also, since the Euclidean it is UV boundary should contain the Gibbon-Hawking term, as well as some boundary counted terms, in order to perform holographic normalization. And then we can compute this on-cell action either numerically or analytically using some approximations. And one typically finds a positive on-cell action for the wormhole. So since we have e to the minus s Euclidean, we find a reasonable probability that this is smaller than 1. And this way, due to the ADS asymptotics, we evaded the issue of the no-boundary proposal. Moreover, depending on the potential, we can find a proper potential so that the universe prefers to nucleate high up in the potential and then follows roll trajectory. This wasn't the case for the no-boundary proposal. Now, moreover, we can connect our model with phenomenological models of inflation. For example, we did this for Higgs inflation. So the Higgs boson is the only experimentally observed scalar particle in nature and could perhaps also play the role of the inflaton. A class of models of inflation that conform very well with observations are the so-called Higgs inflation. And these models essentially include a non-minimal coupling term to the Einstein-Higgs action in the Jordan frame. And this coupling psi, if it goes to infinity, this Higgs inflation model is reduced to the R-squared model of Starobinsky. Such terms typically appear when we're considering loop corrections to the effective action. And currently, the central experimental values of the Higgs and the top mass favor a standard model metastability. So essentially, the Higgs effective potential turns negative at high energies or field values when we include the loop corrections. So if one does a transformation to go back to the Einstein frame and to a canonically normalized scalar field chi of phi, one finds a potential of the Higgs type for small values of this chi and of the zero roll type at inflationary chi. And this has a negative true minimum at very high energies or field values. Now, our particular Higgs inflation model also admits Euclidean ADS wineglass wormhole solutions as long as there is a dominant magnetic radiation component in the early universe. Now, one can compute the potential on the inflationary plateau region for this model approximately, in this 10 to the minus 10 and Planck to the fourth. And for n star 60 folds of inflation, we can obtain the values of the amplitude of the scalar amplitude, the spectral index, and the tensor to scalar ratio, and we can match them with experimental values for this. And we can see that our proposal can be realized in a phenomenological model that is consistent with current experimental or observational data, both from high energy and cosmological astrophysical experiments. Now, let me briefly mention our work in progress about computing cosmological perturbations in such backgrounds. So, if we don't start, so we saw that, okay, for acquiring this phenomenological model, we needed to have electromagnetic radiation, so it's not compulsory to use a model with axion as we did in the initial proposal. So here we will discuss this case. So in this scenario, we can find an analytic solution for the scale factor by imposing the asymptotic behavior we want to have at each region and matching them. And we have three regions: the asymptotically ADS boundary at tau goes to minus infinity, the local minimum at tau min, and the local maximum where we have Euclidean de Sitter at tau equals 0, after which we will analytically continue. And then we can compute the wave function at tau equals 0 and then propagate it in real time. Now, for a probe scalar, the action is the following, and we can compute by finding what is phi, the wave function in this form. And it turns out that the fluctuation equation is a Hoyne equation for which there is a recursive relation to compute its connection formulae using CFT techniques. So essentially, the next step is to compute the power spectrum for the no-boundary and the wormhole proposals and then compare them. Then essentially, we can find the power spectrum by the variance of the wave function. And then we can compute the dimensionless power spectrum. And from this, we can compute the spectral index. And the results for both the no-boundary proposal and our proposal are qualitatively similar. So here we have the massless scalar cosmological perturbations for different angular momenta using the no-boundary proposal. And here we see the same plots for the wineglass wormhole, so we see that they are qualitatively similar. So this is a further check that our proposal could be an alternative to the no-boundary proposal. Let me finish by presenting some future directions and discuss them a bit. So our construction has ADS asymptotics. So it could be amenable to a possible holographic interpretation. But this relies on the fact that we need to understand holographically what are the duals of Euclidean wormholes. And there are various questions regarding this. For example, are there really microscopic UV complete models of Euclidean wormholes, either in holography or in string theory, like to have a string theory on a target space that is a wormhole? And this question is closely related to the factorization problem, where if we had a Lorentzian wormhole, like the Einstein-Roser bridge that connects the two sides of the eternal black hole, we know that this corresponds to entanglement between the two CFTs. But it's not clear what is the analogous statement for Euclidean wormholes, since there is no time and there is no clean definition of entanglement in this scenario. Now, there are various proposals to resolve the factorization problem. So essentially, the factorization problem is the following. So we have, imagine you have a Euclidean wormhole that's asymptotically ADS. We have two ADS asymptotic boundaries, so we have two CFTs that lives at each of the two boundaries. If we had only the CFT pictures, since these are disconnected, we would expect that the system factorizes to the product of the partition function for its system. But from the gravity side, we have these wormhole configurations that connects the two asymptotic boundaries. So there is some tension. So one possibility could be that we see this connected configuration because the quantum gravity path integral corresponds to a form of averaging. Now, what we mean with averaging, it depends, there are various options. For example, in the context of SYK or JT gravity that is dual to a random a matrix model of Hermitian matrices. We have explicit averaging over theories, over random Hamiltonians, or over the coupling constants of the SYK model. But this leads to non-unitary theories, and we know that this is not the case for higher dimensional theories of gravity. For example, in n equals 4 per Young-Mills, that is dual to ADS 5 cross S5, we don't average over anything, and all parameters are fixed. We could have an approximate statistical averaging in the sense that from the gravity side, we do a semiclassical computation, so we don't have a complete knowledge of the UV theories. So essentially, we average over these quantities that we cannot probe from that side, and this leads to the formation of this statistical connected configuration that we could call statistical wormholes. And in this case, they don't have to be saddles. So the question is, do these discussions are related to our cosmology? Is this what happens? Is there some form of averaging that we can see there? Now, there is another proposal to resolve the factorization puzzle, and this is that we have explicit interactions between the two holographic CFTs that live at each of the two boundaries. But these interactions should have a very specific form. They should be soft in the UV and strong in the IR. And the cross correlators, when we have insertions of operators at the one and shifting at the other, should not have short distance singularities, and they should look like averages of lower point correlators in the two individual subsystems. So essentially, for this scenario, the exact Zwinger functional acquires this averaged form, where W is some appropriate weighting factors, and we sum over S, which is some sector, and the sector depends from the exact theory. And essentially, this Zwinger functional comes from a unitary or reflection positive system. For example, this S could refer to the representations of the UN gauge group of the boundary theories. Now, moreover, one would like to have, so our model is bottom-up, but it would be nice if we have at least a supergravity embedding. And it seems that it is possible to find such an embedding. For example, if we use theories with racetrack type of superpotentials, so that they have two exponential terms that are competing. Usually in the KKLT scenarios and related models, one wants to uplift the whole potential to positive values, which is much more difficult, whereas in our case, we just need to uplift a part of it. So in principle, it should be easier and to have better control. Of course, we do not yet know if, I mean, this model can be embedded in supergravity, but it's not clear whether we will find a potential that can actually allow for inflation. And of course, we don't have a clean string theoretic embedding. So essentially, let me summarize what I presented today. So we proposed a new type of wave function for the universe computed from the gravitational path integral with asymptotically Euclidean ADS boundary conditions. In the semiclassical limit, it describes a Euclidean ADS half wormhole geometry. And if the scale factor acquires a local maximum at τ equals 0, or the Z2 reflection point, it gives rise to an expanding universe upon analytic continuation to Lorentzian signature. Now, our proposal can be realized with a non-trivial scalar potential that takes both positive and negative values, and it can be found also in the context of phenomenological models such as Higgs inflation. Our proposal evades some issues of the no-boundary proposal, leading to a well-defined probability, and it can also favor a long-lasting period of inflation if we choose an appropriate scalar potential. And also it raises the interesting possibility of describing the physics of inflating cosmology and their perturbation within the context of holography upon understanding Euclidean wormholes in this setup. Thank you.
So thank you, Olga, for the very nice talk and giving a very wonderful description about the new proposal of addressing the issues of the no boundary. And now the panel is open to the questions. So we have like a few questions. So maybe the audience can ask themselves instead of now writing it in the chat box.
Yeah, now I can see the chat box, but it's better if they ask directly.
Okay.
Okay, there is something in chat. I have a naive doubt. Is it justified to fix both A0 and A prime 0, like fixed position momentum and quantum theory point of view? Okay, here is just solving a second order differential equation where you have two boundary conditions. These are in a semi-classical level, the solutions. It's just to specify the classical geometry.
So I have a question so here basically we are trying to basically just imposing some new kind of boundary choices at the initial some initial period where in order to overcome the issues of no boundary, but so it seems like that it is the model is starting with the ADS, but then it is evolving into a de Sitter phase over time.
Mhm.
And the scalar potential is expected to basically somehow, so we are not putting some lambda by hand, cosmological constant kind of a term in the action by hand, but it is basically the scalar potential whose behavior is such that it is moving like that basically. So it is starting
That's
from
right,
the ADS
yes.
phase and going to a DS phase.
Yes, you need an appropriate potential. That's right. You don't put by hand the cosmological constant.
Uh-huh.
But of course, okay. The no boundary proposal, you have the sphere, so the manifold is smooth. You don't put boundary conditions there. But now you have a Euclidean ADS boundary, and you need to put boundary conditions for your fields at that boundary. So if you choose that the source is 0, then you have good chances that you start from the vacuum.
Uh-huh.
And of course, you could have. It's not that you can fix a unique potential. You can have different potentials that have
Mm-hmm.
the appropriate features to lead to inflation. So there is again some fine tuning, if you wish, as you do in phenomenological models of inflation. But in
Mm-hmm.
phenomenological models of inflation, you fine tune your initial conditions at the point where inflation starts, whereas here you can essentially fix some boundary conditions, but have a mechanism
Mm-hmm.
that leads you to inflation.
Mm-hmm.
You don't do it at the level of inflation, so you have a way to arrive there.
Mm-hmm. It seems or somewhat like I think somewhere you mentioned also about nucleation, like that is happening. Like it's some phase which is a ADS phase and some phase which is a DS phase, and there is some
Mm-hmm.
kind of a Coleman style tunneling happening from negative lambda to a positive lambda via thin wall approximations.
Mm-hmm.
This kind of a solution. And so this phi that so the scalar field probably I may be not appropriately correct because I'm just still trying to understand. But is it some solution which is basically there's a kind of a lambda negative branch and then the lambda positive branch and then a sharp kind, not exactly a sharp, but like a very quick transition happening from lambda negative to lambda positive.
Yeah, I suppose you can also see it that way. Yeah.
Uh-huh.
But yeah, I mean, you can see it also completely classically. You can have complex metrics, you can have a complex, like a potential that can take different values and just smoothly go there.
Mm-hmm, mm-hmm. And this action term that is there in the action, so this is active throughout the whole process, or is it like active in the Euclidean? So ADS branch, like in the early phases when the this thing is this thing, and in the later part when the evolution has taken place, as the scalar field, which is basically dominating and controlling the behavior evolution further on.
So can you repeat that? I'm not sure
So
I
this
understand.
action term that you have in the action,
Which term there?
action term in the action. So if you go in the early parts of the slides, so there is a this action field basically.
The action. Sorry, I didn't understand. Yeah, so the action field is not okay. Let
Yeah,
me
this one,
say
this
something.
term
Yeah,
of
yeah, perfect.
H.
So I didn't mention that to have Euclidean wormholes,
Mm-hmm,
you need to provide the system with negative Euclidean energy.
mm-hmm, mm-hmm,
There are various ways to do this. One way is to add to your action and action field that has a negative kinetic term. So this is how you get the negative Euclidean energy. Or you could have magnetic fluxes that also gives you this Euclidean negative Euclidean energy. Or instead of having three spheres here, you could have three-dimensional hyperboloids that have negative curvature. And then again, you have this. So it's not like the action is not needed. Like in this phenomenology, you just need this negative Euclidean energy. And in this phenomenological model I described here,
Yes.
actually, we don't have an action field. We have
Exactly, yes, yes.
electromagnetic radiation.
Ah.
So it's like there are different systems you can realize such configurations.
So in this later part of the talk, when you are discussing about these phenomenological models, which involves the Kashnikov models and Higgs inflation, this thing. So I guess that is basically something which is along with the action field action, or is it just on its own? It will just provide the wormhole solution, giving Euclidean wormhole plus evolving universe. So these kind of these kind of in this slide. So like
in this slide, essentially you need well, okay, this is simpler because it's just the electromagnetic radiation and the scalar field, minimally coupled. But here the difference is that you have a Higgs field and you have also non-minimal coupling for the scalar field, essentially. So it's just a specific model that can have solutions with a potential that is negative and become positive.
Yeah. And this non-minimal coupling has to be like very large, seems like.
I mean, if it's very large, you get the Starobinsky model.
Okay. But in this way of doing things, one overcomes the issues of the no boundary problems that one has. Basically, the paper of Maldacena, where they were talking about some of the problems that they were facing in the actual Hartle-Hawking no boundary proposal.
Yes, because well, as I was showing here, so essentially when you compute the wave function in this WKB approximation, you compute the exponential of minus the Euclidean non-shell action. So for the no boundary proposal, this is Euclidean has a negative sign, so this becomes positive and you have a very large probability, so it means nothing. Whereas if you have Euclidean ADS asymptotics, this also action after you perform holographic normalization is positive. So with this minus here, you get a probability that is less than 1, so it's reasonable. Whereas at the same time, when you go to compute fluctuations, because the no boundary proposal has this issue about probability, but it gives the correct spectrum of primordial fluctuations.
Yes.
So in our proposal, you have the Euclidean ADS asymptotics that helps you with computing a reasonable probability. But at tau equals 0, where you go to compute the fluctuations, it resembles very much, and at late times, like after tau equals 0, when you analytically continue, it resembles what you get from the no boundary proposal. So you have also a reasonable spectrum for a reasonable answer for the spectrum of primordial perturbations. So that's the issue. What you trade off is that now you need to put the boundary conditions on your Euclidean ADS boundary. That's it basically. And okay, if you want to have a holographic perspective, because these are all semi-classical, you have to find a way to embed this Euclidean wormholes in string theory and understand what they mean holographically before you try to understand from that perspective cosmology as well, which, yeah, it's not something that is settled, I would say.
Okay. So let's see if there are any further questions.
So I wanted to,
Yes.
yeah. First of all, thanks for nice talk. And
Thank you.
actually, it's not a question; it's a remark.
Mhm.
In this business, wormhole things very important stability issue. And we tried hard, and what we could analyze is giving Strominger type wormholes stability. But this expanding or wine glass shaped wormholes we could not analyze, and nobody till
Yeah.
now, because there is some stupid problem. It's similar to analyzing negative modes of a bounce, which is from metastable vacuum decay. But okay, there is some problem which does not allow to analyze this corresponding equations. So it would be nice if someone comes with new ideas and
Yeah.
we can understand negative modes of these wine glass wormholes.
Yeah, I totally agree. We also haven't been. We know that
Did
it's a
you
very
try?
hard
Did you
problem, so
try?
we haven't really tried. But
Mhm.
yeah, I agree with you. It's important that this should be done because yes, exactly. I don't know if the solutions are stable or yeah,
Yeah.
or how I can. Yeah.
Yeah, that's a very interesting point.
Yeah.
Okay, let's see if there are any further questions. So I don't see anything in the chat box. So if not, then maybe let's just thank the speaker again for the wonderful and beautiful talk and a nice proposal of evolution of the universe. So thanks, Olga,
Thank you
very
very
much for
much.
the coming
Thank you
and
too.
agreeing to give a talk. And so hope to see you again sometime.
I hope so too. Thank you again.
Yeah, thanks. Bye bye.
Thank you. Bye.